Consider the RC circuit shown, where R1 is 1500 ohms, R2 is 2550 ohms, and the capacitance of the capacitor is 2 microfarads. When the switch is closed, the current will vary with time as shown in the figure in the middle. What is the time constant for this circuit? Alright, so it's worth noting that 1 over E is approximately 0.37 or 37%. But 1 minus 1 over E, therefore, is 0.63 or 63%. Now the time constant can be thought of in a couple of different ways. A time constant can be how long it takes for charge to build up to 63% of its final value, which is Q max. And I said in a previous video that this was the time constant, the time it takes to reach that 63%. But the time constant can also be thought of as how long it takes for charge to decay to 37% of its original value. And this is Q initial. For a given RC circuit, these time constants will be the same. So our goal here is to find the time constant. First of all, let's redraw the circuit where it has only one resistor, an equivalent resistance, which I'll call REQ. And this is C. Our equivalent resistance is going to be the sum of the original resistances. So that's 1500 ohms plus 2550 ohms, which is 4050 ohms total. Now, interestingly, this graph is not of the charge on a capacitor. It's of the current, I. And as we saw in the past, once a switch is closed on an RC circuit like this, current will decay to zero slowly. And we want to figure out how long does it take to decay to 37% of its initial value. Well, that time is going to be the time constant tau. And we can find it now by using the time constant formula, R times C. But we want to use the equivalent resistance for this RC circuit. It'll be 4050 times 2 microfarads. Gives us a time constant of 0.0081, and the units will be seconds. So this graph is actually not of seconds. It's actually of time constants. So if one time constant has passed, the current will decay from 100% down to 37%. And if another time constant passes, then it'll decay even more, and then so on and so on.